Okay, so there may or may not be class tomorrow. I honestly don't know, and I won't know until probably yeah, 1 o'clock or something like that. So why don't we assume we're not going to have class tomorrow, and if we are, then I'll send you an email saying we are having class. Okay, so the default will be no class tomorrow unless you get an email from me saying we are having class. I want to go over a couple things on the homework just because I'm seeing some weird things and I'm gonna go over it. And our test is gonna be on
Thursday.
and who's invited?
My people.
My people. Okay. So a couple things. Okay, number one. So these are common homework 2 mistakes. One, okay. Do not give me that.
It doesn't mean anything.
Okay, what do I want to see? Yeah.
Vector lines.
Yes. Actually, really, the notation actually isn't a minor. Really work on having really good, strong notation. The other thing is, yes, I know you can actually sometimes do these things by looking at them and writing down the answer, but actually show work. If I have something where there's just basically that I have, you know, for instance, I have this. And then I get something like, you know, 7i hat plus minus 13j hat plus 20k hat. And if there's no work here, I have no idea what you've got. Okay, so then I will, if I'm starting to not see work, I'll start grading it actually kind of nasty. Because there's nothing for me to look. I don't know what you did. All I know is that the answer is wrong. So always show your work. With number 4, we're going to call number 2. I wanted you to tell me what the curls are, kind of without doing any work. And I want you to kind of understand qualitatively what's going on. So we have this guy. This guy. This one. And then we have this one here. Question is, which ones are the curls are 0? And most people got the answers right. The arguments are a little on the funky side. What did we say a curl is? Remember when we talked about a divergence? What's it just qualitatively? What is the divergence? The divergence is the flux for a tiny little cube, right? So this is, remember, we have this big over here. We look at this tiny little cube. Okay, so this is going to be the flux for a tiny cube. Remember, it's not really per unit volume. That's really what it is qualitative. And so if I wanted you to calculate the flux for these things, what would you do? Well, if you had a tiny little cube here like this, okay, what would be the flux of that tiny little cube? 0? Yeah, because based on the flux coming in, it's saying this flux coming out. If I have one over here, what's going to happen in that case?
Negatives.
It would be positive because you're going to have more coming out than you have going in, so this would be a positive. If I put it over here, what would then happen? Positive. If I put my little cube over here, what would I have? Yeah. 0, because basically anything going out would be what's going in. That's qualitatively what happens. Now with the curl, what did we say qualitatively is a curl?
Like rotation.
For a tiny little, remember we had that arbitrarily oriented rectangular loop. So it's going to be really this quantity here for a tiny loop. Per unit area. Okay. So in a case like this, if I had a tiny little loop like that, what would happen if I integrated along all these sides here like this? What could you say about this contribution compared to that contribution?
They cancel out.
They're going to cancel each other. And these two would have nothing here. If I had one over here, a tiny little loop like this, what would happen? Same thing. Yeah, contributions on this side would cancel the contributions on that side. If I come over here, I look at a tiny little loop like this and go around it here like that, what's happening?
All the contributions are canceled.
Yeah, all those contributions are going to cancel here. But if I come over here and look at a little square, what's going to happen?
They're gonna add up.
Yeah, you're gonna get contributions from all these sides here like that. So that's kind of qualitatively what you want to, this guy's here. So often by looking at what that field looks like, without doing even any calculations, you can have a good idea about whether you're gonna have a curl or not. So if you're a mechanical engineer, and you're dealing with basically irrotational flow, what is irrotational flow? You may not know because you don't have mechanical engineers. Okay. Basically, you don't want vortices here. So which one do you have to kill? You have to kill this guy. That'd be a vortex. Basically, these circles here, these whirlpools, they're vortices here. So if you have irrotational flow, what do you want the velocity? What do you know about the curl of the velocity? The curl of the velocity, it better be zero. Okay. Okay, so there's that. With number 3, again, just show more work. Oh, also let's talk about the y component here, because I think there's just a lot of y components. So if you have this right here. And then we have this guy was here's this guy here. This is number 3. Frequently called number 4. Let's look at the y component for this guy. So when you do the y component, so the j is going to be what? You cross off this column, you cross off this row, and you look at this determinant here like that. Now what happens when you get over here to j?
Minus j.
You get a minus j,
And you do the same.
and then you cross off this column, you cross off this row, and then what are you going to do?
This is a derivative of x with the.
This acting on this, and this acting on this.
Is that
the one?
I don't know.
Oh, actually, this is I can. Sorry.
I was really confused.
So what's gonna happen? You cross off this column here, you cross off this column here, then you look at the determinant form of this. So what is it gonna be? It's gonna be this acting on this minus this acting on this. You can get another, so you can get the 0 minus uses this acting on this. Minus partially is the median of this guy here. Okay, that makes sense? So you get this other minus and coming in from doing that diagonal this way. That makes sense? Okay. With number 5, there's just kind of a subtle point here. Again, the hardest thing in life is minus signs. Number 5, you have this loop here, you're going around here like that. And you're calculating this one. And let's give these names. So let's see, this is 2, 3, 4, 5, and I'll call this 1, 2. The main ones I want to look at are I want to look at sides 3 and 4. 2 and I think it's actually side 3 is similar with that. So in side 3, what do you do?
I don't remember. Side 3,
It's gonna be V dotted, so this is side 3. What is my D algebra? I'm going that nice.
J hat.
D, Y, J hat. And I can put a minus on here like that. Now, if I do it like this, what are my limits here then?
From 5 to 4.
It's actually gonna be the 4 to 5.
But you can do from 5 to 4. And you just
Okay, if you go, this is what it's gonna have to be here since I've automatically put in the minus.
Yeah.
Now, if I go like this, if I say I'm gonna go from 5 to 4.
It's gonna give you a negative result.
No, then what does this one have to be here? This can't be my DY, DL. Then I have to write this as DYJ.
Yeah.
Because I either have to come from the minus sign here, and then go from 4 to 5, or I do it this way, going from 5 to 4 this
That'd be funny.
way. Okay, don't do this, that's putting in two minus signs. Okay, that's actually a really simple point. Okay. And then again, with this guy here, same problem. And most people did this right, but there's some steps skipped. Actually, say what this dA vector is. What would be the dA vector for that? Remember, this is z,
dy dt.
this is y, this is x. That would be what?
dy dt.
dy dz I have.
Okay.
And so when you dot this into, you're going to call it the x component of only the x component of that area. All right. That makes sense? Questions? Okay, now let's talk about number 6. There's a lot of stuff going on with number 6. Okay. There are some advantages to having you do this the painful way because you have to understand what these things are. I mean, at least we tried. Okay. First of all, the most common thing was that this number 6 of this whole the most common mistake was again, I don't mind if you work together, but just as your parents say, if your friend jumped off a cliff, would you jump off a cliff? Okay. So if your friend tells you that this is 0, would you randomly then conclude that your friend is all telling you the truth? Okay. Okay. So for some reason, this randomly became 0. No. Okay. Well, let's work these out. Okay, let's take out this one here. What is this guy here? Which is what?
The 6 is right there.
Which is this guy here. What is this acting on?
The v.
V. What is V? Vx I hat plus Vy j hat plus Vz k hat. This is going to result in how many terms? This will result in 9 terms. Okay, you have this acting on here. I hat. This acting on here. To be a j hat. Plus 7 other terms. Does that make sense? Okay, it's going to be this awful rhyme section. I'm talking about this fellow here. That's a divergence, and what does that equal?
Recurrent.
Okay, what does it equal?
The partial of dx versus
Dx
of
is
x, partial of dy with respect to y, partial of d with respect to z.
And then you're taking the gradient of this. Okay, what is our gradient operator? Our gradient operator is I hat partial of respect to x plus j hat partial with respect to y plus k hat partial with respect to z. And this acts on this guy here. And this is going to result in how many terms? 9. Okay, so you get these 9 terms minus this 9 terms, and it's going to be awful. Okay. And then what happens here? Then this part here wasn't too bad, except it magically became 0. Okay, so everyone more or less had the curl correct, and then it kind of went funky on this part here. Okay, so what does this mean here? If you'd actually go through and work it out explicitly. Okay, so what is your curl of V? Curl of V is I hat, j hat, k hat. Partial respect x, partial respect y, partial respect z. I won't work out the whole thing. Vx, vy, vz. So if you look at the I hat here, I hat is what? This acting on here. Minus this acting on here. And then the y and the z. That makes sense? Now, if you're taking the curl of this, now I'm taking the curl of the curl. This is I hat, j hat, k hat, partial respect to x, partial respect to y, partial with respect to Z. What goes in for here?
Yeah, I, J, and K hat component Z distribution.
Yeah, this whole piece here has to go into here. Okay, so this would be that partial of VZ, respect to Y, minus partial VY, respect to Z. And so on for the other terms. That makes sense? Yep.
Yeah, I just named it a new vector, vector A, and it works.
Perfectly fine.
Perfect.
That makes sense? Okay. And then, let's just one more. Yeah, number 7, everything was fine with the exception of there was just the magically equaled 0 without explanation. Okay, so we have this guy here, we have the curl of the curl. I mean the the divergence of the curl. This one actually does equal 0. Okay. So what do we have here? This is going to be your partial of the x component here, so that's y. Z. Most of it is like that, that's perfectly fine. Okay, then you can put in the x components here, so I just, since I just had one component here, I'll put that in here. And then this is your partial VZ, it's right to y, minus the partial Vy, is right to z. And then the other terms here. And then all of a sudden, once you had the other terms, this was in magically 0. Okay, put in a little more effort here. What's actually happening here? What do you know about the mixed derivatives here? But it doesn't matter the order you write. So what happens here, actually go through and take another line here, actually kind of switch the order and show how to explicitly cancels the other term. Okay? So just be detailed in what you're doing. I want precision. Okay, that makes sense? Any questions? Okay, so that said, let's go on and start making circular polarized light. Okay, this is where you're gonna have to channel your inner artist, because there's gonna be a lot of inner artists that actually be channeling. Okay. Start watching all those old Bob Ross videos of him painting and stuff. You're gonna need that. Practice the phrase happy little trees. Okay, so we had a couple things to begin with. Am I still clear? I am still clear. Okay, so we had index refraction. Okay, and how did we define the index refraction from the fluid? Simply the speed of light in the vacuum over the speed of the material. And we said that for what's going to happen in all cases, with the exception of when it doesn't, this is always going to be greater than 1. Greater than or equal. Okay. There'll be a couple cases where it's less than 1, and that's going to be at some point I'll try to give them the whole idea of what the difference between group velocity and phase velocity. It's a subtle difference. We're gonna have that. Now, what did we say happens here? We said that the speed of light in a material is f times lambda naught. So let's draw a little picture here. Here's our material here. Here's our little wavelength going through like this. This is lambda naught. Lambda naught is going to be the wavelength in the material. I mean, in the vacuum. Then we're going to get this. And we found it here, there. This is like. So, what did we say is going to happen in the material? This is going to be F, because what doesn't change? The frequency doesn't change, as it refers to how the electric field is oscillating. That doesn't change. And this is over lambda. The S cancel. And so if I solve this, then for lambda, so lambda equals lambda naught over here. So your wavelength actually gets smaller. That makes sense? When it comes back out, then it goes back to the original net. Now, what would happen if we had a material like this? Suppose we have material. So here are my little atoms in the material. Here are the atoms in my material. And that is still showing up fine. And I'm going to then connect these by springs like this. So these are all connected by springs. Well, let's say in the other direction, we have different types of springs. In other words, maybe I have this K, I'll call this K1. These are all K1s. This all K1s in the vertical direction. And maybe in the horizontal direction, maybe it's different. I'll call these K2s. K2. Yeah. So I can imagine this material here is basically having different springs connecting them in vertical and horizontal direction. So what does that mean here? What that means here is that the oscillation horizontally and the oscillation vertically are going to be different. That you're going to have. And what we're going to find out, this isn't quite obvious to us yet, but what we're going to find out is that these spring constants here, when you actually go through and look at them here, that's actually going to affect what this index of refraction is going to be. So what's going to happen here is I can have one index of refraction in the vertical direction and another index of refraction actually in the horizontal direction. I can have two different indices, two different index of refractions. What's going to happen is that the index of refraction in the vertical and horizontal directions may be different. Okay, so for example, I might have one in the vertical direction, maybe this is going to be 1.5. And maybe one in the horizontal direction, maybe this is going to be 1.4. Okay. And which one is the wave moving faster? So this is an example. So is the wave moving faster in the horizontal direction or faster in the horizontal direction? Vertical or horizontal?
Horizontal.
Okay. How come?
It's inversely proportionate to.
Yeah, the smaller this gets, what does it mean? The faster it gets. So this right here, this is going to be fast. So the way this is going to be fast. This right here, this is going to be slow. And so we're going to give these names. I'm going to call this one N sub S, and this one N sub F. Okay, so I can have a fast index, I can have a slow index. So what would happen if I have this? Is that still good here? That's getting a little, that's okay. So suppose we have crystal like we call this the N fast axis. And this will be the N slow axis. I have one like that. So that's going to be my crystal. And let's say I have a wave. That wave is coming this way. This is at a 45-degree angle. This is my incident. Wait. Okay. The question is, what's going to happen there? Let's draw a little picture of this. So I'm gonna have my light like this. Okay. What can I always do to light? I can break it up into components. So I can break it up into. Let's see what the easiest way to do this. Let me just go with this. These components like that. And I think I wanna. I'm gonna take this one here. I'm gonna write it like, I'll draw it like this. This would show better. This angle right here is 45 degrees. Here's my slow and fast. Let's get this. So I have this picture here. So if I were to actually draw this, what this is going to look like is this. That's my vertical wave, and this is my corresponding horizontal wave. This is my N vertical, and my E vertical. This is my E horizontal. And this right here, that is my 45-degree angle. This is my electric field. Does that make sense? We're good with that? Okay. Now this hits in this crystal here. Let's give these some points here. So I'm going to call this here point A. I'm going to call this point B. So right here, what can you say about A and B? They're doing the same thing. So in other words, right here, these points here, they're actually going to be oscillating like that. Whatever one does, the other does. So we're going to say they're in phase. So A and B are in phase. And since this is a 45-degree angle, what do I know about the amplitude of the vertical and the amplitude of the horizontal?
Equal.
They're equal. They have the same amplitude. Same horizontal and vertical. Now the question is, what happens when it comes out of the crystal? So let's actually go through this. So here's my vertical. Here's my horizontal. It hits the crystal. What does this one see? It sees the fast index. This one sees the slow index. So if it hits like this in phase, what's going to happen? Yeah, I'm actually going to develop a phase difference between those two. Does that make sense? Because this one's moving fast as it hits the crystal. Since this one's moving faster, then you get this, you're going to get a phase difference. That makes sense? When they come out, they're going to retain that phase difference. Now, let's say that this is so thick. This is actually going to induce basically a quarter wavelength between the two. So the crystal is thick enough that the horizontal and vertical components get a quarter wavelength out of phase. And what would that look like? That means when I draw it over here, it's a light. But if I'm here, when this is A, where's B going to be in this picture? A gets ahead, so B is going to have to be, so if this is A, B is going to have to be like that. And this little distance here. That little distance here has to be a quarter of a wavelength. If I to draw this. I'm gonna have something like that, and this is gonna come back here like that. And it's gonna go down like this. I'm gonna extend it here, so it's like that. Okay. So the easiest way I think to draw this is if you draw this being A, do that first. Put a little line here. That line has to be quarter of a wavelength. And then draw your B here. This is your B. And then kind of draw the rest of the way. Okay? Does that make sense? Now, if you lived here, so let's say you're here. You live here, and that wave is hitting. What would you see the electric field do? So you're here, you're in a fixed spot. Am I still? I'm still on here. Okay. When that wave hits you, this electric field's doing what? Right here. It's going down. And then what happens? As this wave comes, what's going to happen now? It comes that way. It's going to be going into the board here. And then up. And then out. So if you're here, what are you seeing that electric field do?
Move kind of like a square almost. Or a circle.
You're going to actually see it moving in a circle. That makes sense?
Yeah.
So you would say you have polarized light, but you would say you have right circular polarized light. This is called right circular polarized. Well, this here.
I have a question.
Yep.
For the wave with the A and B, are you drawing the like the whole like EM leg?
Actually,
just
hang on.
are we just thinking about that?
Hang on before we forget.
Yeah.
Hang up the word right here.
Okay.
There's something I'm doing. Okay, now go on to the question.
I was just wondering, since you were talking about the electrical field, is all the same for the magnetic field, or are you drawing them together?
I'm not drawing the magnetic field here because there's only one reason why.
Because they would overlap.
But it'd become a really, really hideousness.
Okay.
So I'm doing this right here. I'm just drawing
Just talking about the
the E field. The
Okay.
magnetic field would actually have to be coming perpendicular like this. Be perpendicular to this guy.
Okay. That was my question. Thank you.
That makes sense?
So we're just talking about the components of the E.
Only the E field I'm drawing here. This is only E. Okay.
Okay, that makes sense.
Now the question is this going to be right circular polarized light or left circular polarized light? Now here's the problem. There is no entirely universally accepted sign convention for right or left circular polarized light. So what I call right, somebody might call left. What I call left, somebody might call right. I'm going to tell you the one I learned in grad school. And I think it's probably the dominant one, but this is going to be the one I learned in grad school. So this is what you do. Imagine you could take a picture of this wave. So if I could come over here, I take a picture of this wave. So now this is fixed in time. Right? It's just a picture of a wave. That wave is moving this way. You take your right and left hand and point your thumbs in the direction the wave goes. So in both cases, since the wave is going that way, my thumbs would have to be going this way. Start on the left end, point your fingers in the direction of E and see which way, as you go along here, the E bends. So here the E is coming out. So I could go like this in both cases here. Right? But now I'm coming in here, what happens here? The E is going up. Okay, which is the only hand that works? Only this one here. So if I go here, my hands wrap in the direction that as I scan along here, my fingers are wrapping this way. I can use my left hand. So this is going to be left circular polarized light.
How do you know when to take the snapshot?
What?
Like the picture.
You can take it at any time. Basically, once you draw it, consider that the snapshot.
Could you draw right circular as polarized?
Yes, because we're going to do it now. Okay, now tell me how to make right circular polarized light. There's two things I can do.
You could shift land over to the other side.
I agree, but how are we going to make it?
No, you just like take A and like change the shift.
Well, I agree, but tell me what to do in this case. I put you in a lab. Give you everything you need for circular.
So basically switch the index fast and the index slow.
I can switch these, I could rotate my crystal by 90 degrees, that will work. Or,
Change the incident display.
yeah, now have it 45 degree this way,
45 the other one.
45 the other way. Either one will give you the same answer here. Which one do you want to do?
Changes the light.
Okay, all you would, we'll go through the whole mechanism of making it. So do you want to, let's rotate our crystal. But I can do it the other way as well. So if I had this, so I'm gonna set on my light, so you want to still draw this. That's not a sad. That's not a happy little tree. That's a happy little tree. Okay. So here's my A. And here's my B. And this right here is my. This is my E. And this is my 45 degree. I'm gonna draw my crystal. Now I'm gonna make it and slow. And this getting fast. Now this crystal here, since it's getting a quarter wave out of phase, you call a quarter wave. So this right here is called a quarter wave fleet. Because those two components are going to get out of phase by a quarter wave. So let's go through and act it out again. A wave hits like this, these are in phase. Now what's going to happen in this crystal here? This sees the horizontal component sees the fast. The vertical component sees. So when it hits like that, what's going to happen? And that's going to go out like this, right? B is going to get ahead of A by a quarter wave. Why? Because it's a quarter wave flow. If I were to draw this guy here, this is going to be B. And then where would A be?
Being on it, the corner.
I would come back here, quarter wavelength. And this is going to be my A. Okay. And then if I put in my wave, what am I going to have? I'm going to go this. That. Now, how am I going to do the other part? This is going to come out and feel like this, and then hit here like that, and go back like this. And have that type of thing. Okay. Now, is that right or left circular polarized light? And then come over here, click. I've taken my snapshot. The wave is going this way, so I point both my thumbs in that direction here. I start on the left end, and the E is going up. So I go like this, both my hands go up. Now the question is, when I move over here to B, which finger is bending the direction of B? My right is going to go. That makes sense?
Yeah.
Okay.
Oh, I got a question. No, it's about like it's about the way it rotates. Like
Yeah.
I can visualize it like rotating counterclockwise. Can I just say
Well, counterclockwise relative to what? I mean, this is why there's
like relative to, oh, that's right. I mean, I just like see the wave coming at me.
Do it this convention. I'm teaching you here.
Yeah, no, I'm not saying you're
Okay.
but I'm just trying to
I
say
mean, well, there's no right or wrong. It's just a convention. I'm just.
okay,
I want us all to use the same convention.
okay.
I don't want the junior convention.
There's
And then there's that convention. And then, no. I can only do one convention at a time. Okay. That makes sense? So this would be what? This would be right circular polarized light. This is right. That was This is right, yeah. Right, circular, polarized light. That makes sense? Now, what would happen if I didn't have a 45-degree angle? What would happen if instead I had, let's say, a 20-degree angle? If instead if I had this, so I'm gonna have the same thing. Slow, fast. Now I'm gonna have this. Now I have a 20-degree. What's gonna happen here?
Doesn't it just mean that, like the Y component of the EM wave is just dominant compared to the X?
So let's draw. It's gonna look just like this, but what's the difference? This is gonna be this one here. So what do we have here? In this case here, you have a really, really big vertical component, with a really, really tiny horizontal component. It hits the crystal. Which one moves first? Faster.
The horizontal.
The horizontal gets ahead, so we're gonna get that type of thing.
So
So
this
if I had to go through and draw this guy. Now this guy here, this might be. Where's that? And then this right here is my A. So if I to draw this guy, it's gonna be this guy here. And then what do I have then for this? I'm gonna have. Here, and then back. Here, and this is gonna come out like that. So here's this E this way. And here's the E this way. So what is that gonna be? You live here. You see that way finance you, what are you gonna
That's
say?
right. Right.
Initially, it's gonna be really, really big. Right, because this is gonna hit you then. Really, really small this way. This is, then it's gonna go way, way down. So what are you gonna see that you should do?
Right circle is polarized.
You're gonna be seeing it go like this. Is that a circle?
Oh no, it's the nil.
That's an ellipse. So this would be right elliptically polarized light.
So it's just circular when it's 45-degree angle. So most of the time it's elliptical.
What's fun that I said about?
Yeah.
Okay, does that make sense? Okay. Again, you need a quarter wave put. So to get circular polarized light, we're gonna call it quits and we'll pick up class on either tomorrow or on Wednesday. I will have a makeup class at some point to make up for this. Which is what I call it. Yes,
What is the application of like circular and elliptically polarized light?
hold that thought. Okay. We're not gonna do, I'm not gonna answer the question, I'm just telling you to hold that thought.
Alright,
Well, you can do a lot of things. So today. Circular polarized light. What do? You start with one. You send unpolarized light of intensity I naught through a linear polarizer at 45 degrees. And again, the 45 is referring basically to the fast and slow axes of the thing. So send unpolarized light intensity I naught through a linear polarizer at 45 degrees. What would that be? That would be our light coming in this way. This is our I naught. Here's your linear polarizer. 45 degrees. It could be the other way, 45 degrees. What does that guarantee over here?
one single.
What's the only thing that comes out of linear polarized? Linear polarized light
Incidents.
at the same angle as the transmission axis here. So you basically have to have then linear polarized light drawn in over here like this. Maybe like this, where here is my vertical component, and here's my horizontal component. This is my action. But E would be going this way. What do you know about the intensity? The intensity when you send unpolarized light through a linear polarizer is we'll lose half the intensity. Second, send the linear polarized light 45 degrees through a quarter wavelength. So if you draw this picture here, this A, B, here's my fast axis, here's my slow axis. That's gonna give me this. Okay. What happens to the intensity?
Remain the same.
It's gonna be the same. The intensity won't change. And that is how you make circular polarized light. You want it to be elliptically polarized,
Just change the angle.
just change the angle of that first linear polarizer. And you have elliptically polarized light. Okay,
What is the application of linear polarized?
that'll be the next class. Okay. Okay. One thing, now I don't know if it's necessarily done this way, but I heard it was, but I've checked and I don't think it is. For entertainment, I've heard they just use linear polarized light, but I thought somebody told me to use circular polarized light. For entertainment, 3D glasses. Yeah, how do 3D how do 3D movies work?
Wear glasses.
Yeah. Sure, but I mean, but right? If you go like, if I shut one eye, I put my finger there, and if I go like this, and toggle between the two things, I can see my the finger move. So what happens basically? And don't ask me how this happens biologically. This eye here takes one image. This eye here takes another image. You go in the back of the brain, and somehow your brain constructs this 3D picture of it, which is just I just find amazing that that does that. So what happens here? You have a screen that has a flat image on it. So I'm going to make a 3D image of it. You basically film something this way. You film something this way, and then you basically impose those two pictures on the same thing. But what do? You have them in different polarized lights. Okay, you have one of them be polarized this way, one of them be polarized this way. Or what you do, this is what I thought they did, but somebody told me they don't. I thought one of them was right circular polarized, and the other was less circular polarized. And what I'm going to show you is that you can actually have a detector for right polarized light with circular polarized light. But what happens is, if you just take a polarized light like that, and you have on your glasses, the image basically that corresponds to this is going through here, and the image that corresponds to this is coming through here like that, and then your brain then basically feeding the image. So that's one application. But also what happens is when you have a lot of, there's what are called right and left-handed molecules. Depending on when you send it light, it'll actually rotate. You can get basically different amounts of bright or left circular polarized light coming out. So by looking at the amount of bright or less circular polarized light, you can start determining basically the concentration of what's in a lot of these materials.
Interesting.
Okay, we're done for the day.
You're in the office.
Yeah, but it is.